Good morning, myself Kajal. I am a student of BSc Chemistry on the first year. Today topic is periodic properties. The periodic table is a framework upon which much of our understanding of inorganic chemistry is based. In this chapter, we will provide the basic property that you will need for more detailed discussion of main group element in later chapter. Long form of the periodic table. In the modern periodic table, the elements are arranged in order of their increasing atomic number, the number of protons. There has been several designs of the table over the year, but the two most common designs are the long form and the short form. The long form of the periodic table show all the elements in numerical order. However, the long form is very inclined and a Commerson diagram because elements from lanthanum to yttrium and from actinium to nobelium show similar chemical behavior. The short form clearly display these two sets of elements in row below the remainder of the table, and resulting space is closed. The new compact short form of the table. The long form of the periodic table consists of horizontal rows called periods and vertical column called groups. The period is comprised of a series of elements, the atom of which possess the same number of electron shell, the principal quantum number n. The number of elements in each period corresponding to the number of electrons required to fill those orbitals. In a particular period, the principal quantum number of the p orbital is the same as that of the s orbital, where the d orbital are 1 less and f orbital are 2 less. The main group corresponding to element in which s and p are being filled. In a periodic table, they are the 7 period, and each period starts with a new principal quantum number. It is important to mention that first 6 periods are full and contain 2, 8, 8, 18, 18, 32 elements respectively, where the 7th period is incomplete and contains 26 elements. It has a maximum capacity of the 32 element. The first 3 periods contain 2, 8, 8 elements are called the short periods, while the next 3 contain 18, 18, 32 elements are called the long periods. The vertical columns are called groups, each group containing the element of similar electronic configuration. For example, all group 1 element have the one outer electron, that is ns1, where n is a principal quantum number. All the elements in group have the similar property. It is important to realize that every element is unique. For example, nitrogen and phosphorus are elements of the same group. Nitrogen gas is very unreactive and phosphorus is highly reactive and spontaneously catch fire in air. There are in total 18 groups in a long form of the periodic table. According to the recommendation of the International Union of Pure and Applied Chemistry (IUPAC), the group of the element are numbered from 1 to 18. Earlierly, the group were numbered from 1 to V111 as a B group. IUPAC has replaced the old system of using a mixture of Roman numericals and letters. This notation caused some of the confusion because of the difference in numbering between USA and rest of the world. As an example, in USA, the group 3rd B referred to the group containing scandium, where in the rest of the world this designation was used for groups starting from boron. Group 1 and Group 2 and Group 13 to 18 represent the main group element. Group 13 to 11 are classified as transition element. In the transition metals, the D block are progressively filled. We shall be focusing in this course on the chemistry of the main group element. The element of the group 12, although included in a transition element, have a very different chemistry. Some of the group that have the good special names, for example, alkali metal group 1, alkaline earth metal group 2, chalcogens group 16, halogens group 17, noble gases group 18. The element of group 11 are called the Coinage metals. The element corresponding to the filling F orbital are called the lanthanoids, and this corresponding to 5F orbital are called the actinoids. Earlierly, these were named lanthanides and actinides, but the ending "ide" is not justified, as "ide" is generally used in the end of the anions, oxide or chloride. Initially, IUPAC suggested the name as lanthanones and actinoids. However, later these were not finally accepted as the ending. On is preferred only for non-metal, for example boron and silicon, etc., where lanthanides and actinides are metallic in nature. Finally, the word lanthanode, actinode is recommended and should be strictly followed. S, P, D, and F block of element. The long form of the periodic table can be conveniently divided into the 4 main blocks: S block element. The element in which last electron enter the s orbital of their outermost energy level are called the s block element. These are two groups in these block with electronic configuration ns1 and ns2. The general electronic configuration is ns1 to 2. P block element. The element in which the last electron enter the p orbital of their outermost energy level are called the p block element. The general electronic configuration of p block element may be written as ns2 and p 1 to 6. All the element of the group 13 to 18 consequent p block element. D block element. The element in which the last electron enter the d orbital of their penultimate last but one energy level constituent d block element. These elements are called the transition metals. It is because these elements symbolize a change in character from metal on one side to the non-metal. Thus these elements lie in between S and P block element and form 10 groups. These groups are named from 3 to 12. The general electronic configuration of D block element may be respectively as n-1, D1 to 10, and S1 to 2. The D block element contains the three complete rows of the 10 element which involve the filling of 3d, 4d and 5d orbital respectively. The elements starting from scandium Z is equal to 21 to zinc 30 constitute the first transition series. Elements starting from yttrium Z39 and ending with cadmium Z48 constitute the second transition series, while elements starting from lanthanum Z is equal to 57, hafnium Z is equal to 72, to mercury Z is equal to 80 is called the third transition series. F block element. The element in which the last electron enter the f orbital of their atoms are called the F block element. The last electron enter into the third to the outermost energy level n-2f. These are two series in this block of element and separated place at the bottom of the periodic table. The first series starting with lanthanum Z is equal to 57 and the element present in this series called the lanthanoids. The second series start with element actinium AC Z is equal to 89 and end up with element LR 103. The element of this series are called actinoids. The general electronic configuration of this element may be represented as n-2 F1 to 14 n-1 D0 to 1 ns2. Effective nuclear charge and Slater rules. We have already discussed that in a multi-electron atoms, the electron in the outermost shell do not experience the full effect of the nucleus. This is primarily because of the interweaving electron that come in the way between the nucleus and the outermost electron of the atom. In other words, the inner core of electron act as a barrier between the nucleus and the outermost electron. As a result, the outer electron experience only a part of the nuclear charge. The actual nuclear charge felt by the outermost electron is called the effective nuclear charge, which is lower than the total effective charge. Since the inner electron serves as a slide or a screen, this effect is called to be the screening or shielding effect. Thus, the effective nuclear charge Z can be easily experienced by subtracting the shielding or screening effect for the inner electrons from the actual nuclear charge as Z star is equal to Z minus S, where Z is a nuclear charge equal to the atomic number and S is a shielding or a screening constant. In 1930, J.C. Slater proposed a set of the empirical rule to calculate the effective nuclear charge. These rules are slowly based upon the penetration power of the various orbital. We have already learned in chapter first that s orbital electron trying to shield the nucleus more effectively than the p electron, which in turn while slide the nucleus more effectively than d electrons. Thus, for a given value of n, the screening constant S varies S greater than P greater than D greater than F. Periodic properties. Atomic properties which can be used to explain periodicity of the chemical and a physical property must also be periodic in nature. We would expect atomic property to be related to the observed periodicity in the electronic configuration of atom. We shall examine four of the important atomic properties that are most useful in explaining chemical and physical property. These are atomic and anic radii, ionization energy, electron affinity, electron negativity. Atomic and ionic radii. Atomic size. One of the most important systematic periodic property is atomic or ionic radii. We have learned in a previous chapter that electrons can be defined only in a term of the probability and therefore there is no real boundary to an atom. In other words, the electron cloud around the nucleus do not have sharp definite boundary. Thus, atoms and ion cannot be regarded as hard ball. How can then we define the size of an atom or ions? There are actually four ways to determine the size of the atom, and to some extent they give the different value. One of the simplest methods to define the atomic radii is to measure the distance between the nucleus and the outermost shell of the atom. Let us take a simple homonuclear diatomic molecule such as chlorine. The radius of the chlorine atom can be determined experimentally by dividing the distance between the center of the two atoms in chlorine molecule by 2. The distance is 2 picometer 200 picometer, so the radius of the chlorine atom is 100 picometer. This distance is called the covalent radius because the atoms are held together by a covalent bond. Similarly, CC distance in diamond is 1.54 Armstrong, 154 picometer. So the radius of the carbon atom is 77 picometer. In order to test the accuracy of this method, we can add them together to estimate the distance between chlorine and carbon in a molecule, saying carbon tetrachloride. The carbon chlorine distance come to be 177, 100 plus 77. This distance is in close agreement with the experimentally determined distance of 176 picometer. The radius of the atom is calculating by measuring the distance between the center of the two atoms in a molecule with the help of the X-ray diffraction or spectral studies. Thus, in case of the homonuclear diatomic molecule, the covalent radii is defined as one half of the distance between the center of nuclei, internuclear distance of the two similar atoms bonded in a molecule. Similarly, in a heteronuclear diatomic molecule, the singly bonded covalent radius of an atom can be calculated by knowing the internuclear distance between the two nuclei and covalent radius of the one other. For example, the internuclear distance between iodine and chlorine is ICl bond is 2.32 angstrom. R iodine plus R chlorine is equal to 2.32 angstrom. Ri plus 1 angstrom is equal to 2.32 angstrom. So Ri is equal to 1.32 angstrom. Thus the covalent radii of iodine is 1.32 angstrom. This approach of determining the radii of atom is applicable in molecular compound of the element that exist as single bonded. The atomic radii of atom which do not form diatomic molecule with single bond are calculated by the indirect method. For example, the single bond radii of nitrogen and oxygen cannot be obtained from the bond length in triple bonded and triple bond and ento molecule or the double bond or double bond O. This is because these molecules contain multiple bonds. The single bond atomic radii of nitrogen can be obtained indirectly. For example, the internuclear distance between carbon nitrogen in CH3NH2 have been found to be 1.47 angstrom. We know that the atomic radii of carbon in diamond 0.77 angstrom. Therefore, the atomic radius of the nitrogen in carbon nitrogen bond is 0.70 angstrom. This simple rule for evaluating the atomic radii is true in case where the bond formed between the atoms are singly covalent. The difference in electronegativity of bonded atom is not so large. However, in case where there is a large difference in the electronegativity, Shockmaker and Stephenson 1941 proposed a new equation for calculating covalent radius. RAB is equal to R of A plus R of B minus C into xi of A minus xi of B, where RAB is the internuclear distance between A and B, Ra is the covalent radii of A, B is the covalent radii of B, xi A is the electronegativity of A, xi B is the electronegativity of B. So is a constant and have the value 0.08, 0.06, 0.04 and 0.02 angstrom for the element second third, fourth, fifth period of the p block element respectively. The carefully inspection relieve that for the main group elements, atomic radii increasing going down the group in a periodic table and decreasing going along the period. This can be easily explained. In going from top to bottom of the periodic table, the outermost electron are placed in orbital with a higher and higher value of the principal quantum number n. The higher the principal quantum number of shell, the higher is the radius of shell, although the charge on the nucleus increases going down a group. The effective nuclear charge, that is actual charge experienced by the outer electron, do not increase as much. For example, the atomic number of lithium is 3 and the atomic number of potassium is 90. The positive charge in the nucleus of a potassium atom is over 6 times as large as the positive charge on the nucleus of a lithium atom. However, the effective nuclear charge that the outer electron in potassium atom feel is less than 3 times the effective nuclear charge that the outer electron of the lithium atom feels. In a potassium atom, there are more electrons between the nucleus and the outer electron to shield the outer electron from the positive charge in the nucleus. The size the increase in size with an increase in principal quantum number predominate over increasing effective nuclear charge and atomic radii increase in going down a group. The atomic radii of main group element decreasing from left to right across the period in a periodic table. The principal quantum number of